Welcome to Acquire Knowledge channel. In this video, we are going to discuss on unit systems in finite element analysis. Even though the concept is demonstrated using the LS-dyna tool, but the core concept is same for all FEA tools available in market. To give a background, the unit system concept is fundamental but a very crucial concept. Ensuring a consistent unit system is paramount while working with any FEA model. To highlight the importance, one example is shown on the right bottom side of this slide, in which in 1999, NASA Mars Climate Orbiter burned up while entering the Martian environment. And the reason was because the engineers failed to convert unit from English to metric. So let's start with this video. Whenever we open tool like LS-dyna, ANSYS, APDL, Abacus, we will see that it doesn't provide an option to enter the unit system. The reason lies in the fundamentals that FEA solvers only understand the values and not the units. To be more specific, computer actually works on the values that is provided from the any FEA tool. Now let's come back to LS-dyna. So to summarize this thing, LS-dyna doesn't have any inbuilt unit system. It's core responsibility of a user to provide and interpret the results in a consistent unit system. Let's take a very quick example. On right, you can see that there are three sets of unit systems that has been provided for you. So I just want to ask, like if I want to go with the third unit system, and if we enter a value of 1, so how much load that solver is going to apply to the model that we are building in LS-dyna. Okay, so the answer is that if we are going to enter a value of 1, based upon the force unit, we can see the force unit based upon the base dimension, it will be kilonewton. So solver will interpret the values or apply the values in a physical sense. Like in physical sense, on simulation model, you are applying a 1 kilonewton of force. Now next few slides we are going to discuss on fundamentals. So you can also skip to the section 3. Check the timestamp provided in the description. Dimensions or units are commonly confused with each other. We can say dimensions are values and unit is something which tells about the reference with respect to which the measurement is carried out. To understand it, let's take a very simple example. So if I ask you, what is the length of this line? Can you define the length without using the unit system? The answer is no. To define any dimensional quantity, we require a dimension plus reference, and that reference is called as unit system. Now, unit can be any established uh, name in engineering practice or some arbitrary name that we give to that unit system. Now, next thing is that to convert one unit system to another unit system, we need some conversion factor. Like for example, I can say that the length of this line is 1 meter. I can also say the length of the line is 1000 mm. So what we are doing is that we are while converting the meter to mm, we are using a conversion factor of 1000. Now we will discuss next in detail on that, like how we usually convert from one unit system to another unit system. Let's take a generic example. Suppose I want to convert the length 1 meter in a user defined unit system test 1. Now the first thing that we need is how those two units are related with each other. Like for example, we can say unit 1 is equal to factor into unit 2. Now let's define the factor as 1 into the power minus 4. So what we can say is that 1 meter is equal to, test 1 is equal to 1 into the power minus 4 meter. Now, if we want to convert the length 1 meter in terms of the new unit system, what we can do is that first we can multiply the numerator and denominator, because we know the conversion factor, that is 1 into the power minus 4. So we can multiply numerator and denominator by 1 into the power minus 4. Now if we take this 1 e to the power minus 4 in the bracket, so it will become 1 into the power 4 into m, that is a meter, and it is multiplying with some coefficient 1 into the power 4. And we know based upon the first standard that we set, that how we want to correlate these two unit system. We can say now that 1 meter is equal to 1 into the power 4 into test 1. Now this test 1 is simply equal to 1 into the power minus 4 into meter. Now, in most of the cases, when you look at the literature, while working with the different unit system, you will see that they are providing some type of conversion factors. So this conversion factor concept is quite important, and we have to actually, while inputting any data to the simulation, if we are planning to work in the different unit system, we have to use those conversion factors to reconvert the data in the current unit system that we are planning to work with. Let's now move to the actual modeling environment. Suppose we want to model a block that is subjected to load on one side, fixed at another end. It is made up of aluminum grade materials. So once you open the pre-post, it will look like this. Nothing but an option only to enter values. Okay. Now at this point we are clear that it's the sole responsibility of a user to ensure a consistent unit system or a correct input that is provided to the simulation, and we have to interpret the results accordingly in the consistent unit system that we initially set in the beginning of the model creation. Now this image shows a case in which we plan to use a SI unit system, that is meter, kg and second. So in the material elastic card we can see the density is defined as it is, that is provided, because the data that is provided to us is also in a SI system. So we can directly enter 2700, 7 e to the power 10, and if we look at the loading graph, so the pressure is given as 7 e to 70 e to the power 5. So we are applying the pressure as it is, and while interpreting the results, whatever the result deformations that we are getting, those deformations are again in terms of metric unit system. So we can say that the maximum deformation that is going to happen in this case is 2.173 e to the power minus 5 meter. Next, assume a situation in which you received the model or created a geometry in LS prepost, and after measuring the distance, you are getting the values shown on the right. Like for first block, you are getting a value of 1, another you are getting a value of 100, and in third you are getting a value of 1000. Now, the question that I want to ask you, like what will be the base dimension for length that you are going to choose for each cases? So in this case, we already know that our block length is 1 meter. So in simulation environment, if you are going to get these values, what will be the base dimensions that you are going to start? Now pause and think. Now to answer this, the answer to this question is that if we look at the first, that is it's giving me a value of 1. It means that I can start with my SI unit system, length based unit as a meter. Another case, I'm getting a value of 100. Now, if I compare this 100 with meter, I know that 100 centimeter is going to be equal to 1 meter. So I can set the length unit system for the second case as a centimeter. Third is 1000. So 1000 mm is equal to 1 meter, that we already know. Then we can set the unit system for the third case as a unit system. So this is one way, like whenever you are getting the geometry or if you are creating the CAD geometry, it's one way to always ensure that what is the expected length of the model. And in the simulation environment, we can play around with the unit system in such a way that they will mimic the same situation. Choice of unit system is going to affect the material data, support supplied loading, or any other conditions, or like if you want to apply a prescribed displacement. So it's going to affect all those things. So let's understand this thing in detail. We are going to discuss only on a structural modeling. In a structural problem, the following quantities are of concern, like mass, length, time, force, pressure, and energy. Now, if we decide the unit for any of these three quantities, what we can do is that we can derive the unit for other remaining quantities. Base dimensions are mass, length, and time. So this force, stress, and this energy are further broken down into those base units. Like here we can see stress is equal to mass divided by length and time square. Now to understand this thing properly, let's take an example in which we know the CAD that is supplied to us or the CAD that we created is in unit system, and the decision is made to fix the unit system of force as Newton. It means that we are fixing two of the quantities, and Newton. Now at this point we need to fix one additional quantities, because if we know three quantities units, we can derive the unit system for other quantities. Now assume that we are modeling a problem in which the loading is applied in seconds. So we can easily fix the time unit system as a second for this case. Now, if we fix the unit as second, we will get the unit of mass as ton, stress as MPa, Young modulus unit is also of pressure, so it will again in megapascal, and energy will be in millijoules. Now let's check how we come up with this values of the mass as a unit system of mass as a ton and the stresses are as a megapascal. So first thing, we had fixed the unit system of force as a Newton. Now we can write the force as Newton as kg meter per second square. Now length dimension has been set to mm. It means that we can multiply the numerator, because we know that how the meter and mm is correlated with related with each other. So let's multiply the numerator and denominator with 1 e to the power minus 3. And again, if we move this thing into the bracket, so this term will become mm. Time unit was in second. And 1 e to the power 3 kg, if we compare it with the first equation, it will be the mass. Now 1 into the power 3 kg, we know it's ton. So 1 into the power 3 kg. So we can say that the unit system for the mass will become ton. Now next thing is that let's derive the unit system for stress. Now for stress, as we had already decided the mass unit system, length unit system, and second. So base dimensions we are already aware of. We can write stress is equal to, using this formula, m divided by LT square, that is ton by mm second square. Now reconverting the ton into kg, 1 e to the power 3 kg, mm will be 1 e to the power minus 3 meter into per second square. So it will become 1 e to the power 6 kg divided by meter second square. Now we know that kg by meter per second square is nothing but Pascal, and multiplying it by 1 into the power 6 will give us a unit of MPa for the stress. Now let's take the quantity of a steel. We know that steel density is 7830 kg per meter cube. Now if we reconvert this density into the current unit system, that is ton, mm, and second, that we are planning to work, we can convert 7830 into 1 into the power minus kg into ton and meter into mm. So we will come up with the value of 7.83 e to the power minus 9 into ton by mm cube. And this is the unit density, so density unit in the current unit system, that is ton, mm, and second. Now just to show you, this is something that value, like whenever you are entering the value in the SI unit system, we enter 78302 e to the power 11 0.3 for modeling this problem that we initially discussed. Now, if we change the unit system to ton, mm, and second, we have to enter the values like this, like 7.83 e to the power minus 9, that is coming from here. Then whatever the Young modulus value that was given in Pascal, we have to reconvert that value into a megapascal. So it will become 2.07 e to the power 5. And Poisson's ratio is dimensionless, so it will remain 0.3. Now, in the main model, we were applying a value of 70 into e to the power 5 Pascal. That was the pressure loading. So when we apply the same loading in the current unit system, we have to only enter a value of 7. Okay. We should not enter a value of 7 e to the power 6. We have to enter a value of 7. It will automatically interpret that 1 MPa unit system the user is planning to work with. Simulation requirement force the user to work in different geometrical scale dimensions. So these are four cases spanning from macro to micro scale model. Now there is a concept of round off and truncation error, which is due to floating point number in FEA. The thumb rule to avoid this is to choose a unit system which causes the input to the simulation close to unity. It's not actually always possible, but we should try to provide the input that is as close to unity, and that will avoid the chances of round off and the truncation error into the simulation. Like if for this case, like if you look the metric scale, like if you want to simulate the full dynamics of a tractor, it means that we have to actually model everything, but tractor also consists of computational domain that are very small in size. So that can again cause some round off and truncation errors. The second example shows a disc brake example. Now, if you want to further go into what's happening at the material microscopic level, we can also model those things using the RVE approach. Then the nanoscale example. So each working at each level requires a different set of choice of unit systems based upon the geometrical dimension. Now, I provided the link to know further on this. You can refer all these links to understand in detail about the round of truncation error in simulation. I just want to highlight one more thing is that this round off and truncation errors are cumulative in nature. So if you are running a simulation for a longer time, they will get accumulated, and finally it might happen that if the choice of the unit system is not correct, then your final outcome will be drastically different for what is actually expected in the real scenarios. I will also request you to actually try out the previous example that we were discussing, blocks subjected to some pressure in the different unit systems. First take a meter kg and seconds, then take a ton unit system that we were discussing, then micrometer and nanometer unit systems. To continue our discussion, let's take a practical example in which the requirement is to simulate a particulate in LS-dyna. The size of the sphere is 5 nanometer and the applied force is also is nanonewton. Now the first question that I want to ask, you can try it in LS prepost. Can you create a sphere geometry in LS-dyna of order 1 into the power 9? Pause and give a shot. Now think how we can model this problem effectively by playing around with the unit system. I had to just to demonstrate what I did is that I had taken two set of unit system and how the values of the density and the young modulus are going to vary. So we are going to assume that this particulate is made up of structural steel only. So let's start with the first case. So in first case we had fixed the unit of length as a nanometer, time as second, force as a nanonewton. So let's try to derive the mass unit, stress, and the corresponding densities values for the structural steel. So if we write the force, because we have already set the unit as a nanonewton, we can write that nanonewton in form of 1 to the power minus 9 kg meter per second square. And if we are going to further break down and then recompare it with equation number 1, we will see that the mass unit for this specific unit system is going to be in kg. Now, if we do the same thing for stress, because now we already have the three base dimensions that are mass, length, and time. So based upon that, if we further convert all those nanometer into meters and try to see the final unit, then it is going to all the input for the stress, young modulus, and pressures are going to be in gigapascal. Now, if we try to convert the density, that is 7830 kg per meter cube, in new unit system, that is going to be kg divided by Newton meter cube, then the value is going to be 7.83 into e to the power 30. Now, next, if we enter these values, so it is going to look something like this, that is shown on the new unit system values. So density, we have to enter 7.83 e to the power 30. Young modulus, because it's now in gigapascals, so we have to only enter 200. Poisson's ratio is going to be same. Similarly, the loading that was initially 7 e to the power 6 Pascal, for this specific unit system that we are planning to work, the value that we are going to enter into the simulation is going to become 7 e to the power minus 3. Now let's take the second case. In that, only thing that we did is that we had taken the time unit as a microseconds. So if we try to do the same thing, we will come up with the unit of mass as a nanogram. Stress will remain the same, that is gigapascal. Density value will finally come as 7.83 e to the power minus 12. And these are the corresponding values that we have to provide in the simulation. Just to highlight, the loading values that I'm reporting here is based upon the first example of the block that we were discussing. I had not actually taken any load for the spherical geometry, spherical particulate geometry. So it is just to highlight the values, like if we change the unit system, how it is going to get scaled. This is one example that I want to also highlight. This is something that is followed rigorously in industry when we are performing any crash type of simulation. The reason is that the crash type usually happens in microseconds. So time unit they prefer to set in microseconds, and length is mm and mass is kg. So I will request you to try to derive it, even though I had given the solution. So you can see the force, whatever the corresponding force unit that we are going to get after deriving that force unit from this three base dimensions is going to be in kilonewton, then gigapascal, density is going to be in kg per meter mm cube, and energy is going to be kilonewton mm. These are some of the tips and tricks that I want to share. So usually I will suggest, based upon your modeling simulation problem, try to decide, come up with a unit system that is that will give you some input systems that are close to unity, usually or to avoid any floating point errors. Now, if you are planning to do a multi-physics type of simulation, use a consistent unit system throughout all the physics. So if you start with a SI unit system, that is a metric unit system, make sure that for all the physics you are using the same metric system unit. Now, round FLR is cumulative in nature. So in case if you run with some errors like the inertia tensor of nodal body region is too small for the accuracy of computer to handle, try with the double precision solver instead of the single precision solver. Also, I want to highlight, if you work with ANSYS Workbench GUI interface, then these unit systems conversion factors are already included in the tool. So we don't have to actually bother unless and until we are trying to enhance the capabilities using some command snippet or any other scripting. I had also provided this further links like the support database. It consists of 15 units, a set of 15 unit system sets with all the conversion factors. So you can refer it to know more about the floating point arithmetic that leads to round off and truncation errors. Refer to this Wikipedia link. And again, this is a unit converter tool that will be very helpful. So you can just look at this unit conversion tool to see the conversion factors or the corresponding other unit systems. So thanks. I hope that you will like this video. In case if you like this video, please share, subscribe, and like this video so that we will be motivated enough to make new videos for you. Thank you and have a nice day.